Hello everyone, my name is Said Nejati and this is the introductory talk for our paper on machine learning based splitting heuristic for divide and conquer solvers. Divide and conquer SAT solvers accept a Boolean formula phi as an input and split it into several different smaller subformulas and solve the subformulas in parallel using sequential SAT solvers. And the way the splitting works in this scenario is that the solver picks a variable, for example, x, and set it both to true and false, and derives the two subformulas out of that, and then it could further split the resultant formulas into smaller subformulas. And the process of picking these variables to split the formula is called the splitting heuristic. And the general goal of splitting heuristic is to minimize the runtime, of course. But to be able to achieve the minimizing runtime goal of the splitting heuristic, we need to be able to answer this question of how to measure the quality of a splitting variable. So generally, people quantify this using a performance metric function that from a formula phi and a variable within that formula, we assign a real value to each variable. And then the splitting heuristic process becomes picking a variable that minimizes this performance metric. In our work, we define the performance metric to directly be the runtime of splitting the formula phi over a variable v once and solving the resultant subformulas in parallel. But the problem with this formulation is that we need to know the runtime of solving phi and v and phi and negation of v. And in general, predicting the runtime of a solver over any general formula is a very challenging task. But the observation we could make here is that we don't need to know the exact value of the PMs, and we only need to be able to compare the PM values for all of the variables to be able to compare them. So in other words, we don't need to know the 0.98 for V2. We only need to know that PM value of V2 is larger than V1. And we define this pairwise function that given a formula and two variables within that, it compares the PM values of Vi and Vj and gives us a value of 0, 1 based on that. And because it's a 0, 1 output, we could train a binary classifier to approximate this pairwise function. And learning this pairwise function, we could use it as a comparator to find a minimum element in the list of variables that are candidates for splitting. We implemented this system in painless parallel SAT solver framework and compared it with the baseline and state-of-the-art triangling on benchmarks like SAT competition benchmarking cryptographic. And on 16 cores, we could see that we outperformed both state-of-the-art and baseline painless. Thank you very much.
Hello everyone, I am Remy Garcia from Université Côte d'Azur, and I will talk about a branch-bound algorithm to rigorously enclose the range of errors. So first, let's see what exactly is an error. Here, you have a function computed over real numbers. It is continuous and has an infinite number of values. Now, let's compute the same function over floating point numbers. What we get as a result is a discrete function represented by a finite set of points. But even though both functions have the same shape, we can see some big differences between them. So let's focus on the blue square here to see them more clearly. Here, you have in orange the distance between a computation done over floats and the equivalent computation done over reals. It is what we call an error. An error is computed for a given input by doing the difference between the result of the computation done over floats and the result of the computation done over reals. A particular error of interest is the one shown here in pink. We call it the largest absolute error. It occurs for a given input interval given to our function in the worst possible case. In other words, it is the greatest error reachable in absolute values. Now, the focus of our work is to provide an enclosure of the largest absolute error. To do so, we'll compute an under approximation of it and provide input values to make sure it is reachable. while we will also compute an over-approximation of errors. Computing such an enclosure can be seen as an optimization problem, where we will maximize the under-approximation of the largest absolute error. But how do we solve this optimization problem? We start with a model representing the problem we want to solve, and we will give it to our solver Fera, more particularly to the branch and bound algorithm. This algorithm can be divided in two parts, the bounding and the branching. For the bounding part, we first compute an upper bound, which is the over-approximation of our enclosure, with our constraint filtering. We'll also compute the lower bound, which is the under-approximation, with a generate and test. We'll randomly instantiate variables to make sure the error is reachable. We'll also use a local search to explore the search space and try improving the computed lower bound. Once both bounds are computed, we now have an enclosure of the largest absolute error. The next step is to go to branching. First, we need to generate sub-boxes from the current box, and finally select a new box in the list of available boxes to explore. Now the whole process repeats itself until there is no boxes to explore. We now have the best enclosure we can compute of the largest absolute error, and we will output it as a solution alongside the input values for the lower bound.
Hello, my name is Dimosthenis Souros, and our paper is about omissions in constraint acquisition. Constraint programming is considered as one of the foremost paradigms for solving combinatorial problems. The main idea is that the user models the problems he has in mind, and then a CP solver is used to solve the problem. A major bottleneck in the use of constraint programming is modeling. Expressing a combinatorial problem as a constraint network requires considerable expertise in the field. As a result, one of the major challenges in constraint programming research is to automate the modeling process, to efficiently obtain good models of a real problem without relying on expert human modelers. Constraint acquisition is a research area in this direction, aiming at assisting non-expert users to model their problem automatically. In this work, we overcome one more limitation of constraint acquisition in order to make it a useful tool for real applications. Constraint acquisition can be divided in two main types, as we can see here. We have passive acquisition and active acquisition. In passive acquisition, the user gives some examples of solutions and non-solutions of the problem to the acquisition system, and then the system extracts a model that can be derived through these examples. In contrast, in active or interactive acquisition, the system interacts with the user during the acquisition process, posting queries which the user has to answer. The system then extracts the model when it has converged to the target constraint network. Although constraint acquisition has made a lot of progress the last years, there are still several challenges that it needs to overcome. A major limitation of interactive system is the assumption that all the answers of the user are correct and that the user can answer all the queries posed by the system. This is not realistic, as the user may have gaps in her knowledge of the problem, and the user may get confused in a query for several reasons and may prefer to omit it, or otherwise she will answer wrongly. In this work, we deal with a case where the user can't answer some queries. We use omissions, I don't know replies to achieve that, but a critical question that arises with that is it possible to learn something from an omission answer of the user? In more detail about our contributions, we introduce a new type of queries to handle omissions in constraint acquisition and propose two methods to handle I don't know answers. In the first method, the assumption is that the omissions are random events and the reason of the omission cannot be discovered. In our second method, the assumption is that the omissions are related to gaps in the user's knowledge. Both methods have quite good performance when the assumptions made are true. Importantly, our second method is also able to learn the gap in the user's knowledge. For more details, please watch the full presentation. Thank you.
So this talk is going to be about how constraint programming can be used to generate logic programs, and I will in particular focus on probabilistic logic programs. A common example of a probabilistic logic programming language is Problog. And a common example of a program in Problog is called Smokers. You can see how the structure of a program is basically the same as in a typical logic program, but we also have probabilities attached to clauses. And whenever we query a ground atom or a ground formula, instead of a true or false answer, we get a probability in return. Probabilistic logic programming has been used in many different fields, with a lot of applications in robotics, natural language processing, also cancer diagnosis, and data analysis in biology. A lot of inference algorithms have been proposed, but whenever a new algorithm is proposed for inference in probabilistic logic programs, it's typically only compared to other algorithms based on a couple of programs, often just one program with slight variations in between experiments. So this work is supposed to fill this gap and allow people working on inference algorithms to test their algorithms on a wider range of problems. In the full version of this talk, I will describe the main aspects of the constraint model that we use to generate programs. I will give a brief introduction into inference for probabilistic logic programs and show what kind of conclusions we can draw from applying a random program generator to inference algorithms.
Hello, my name is Marco Kleine-Bühning, and I want to give a short introduction of our topic, verifying equivalence properties of neural networks with ReLU activation functions. This is a joint work together with Philipp Kern and Carsten Sins at the KIT. First of all, I want to motivate the formal verification of neural networks. Neural networks are applied in many different fields, but they are increasingly applied in safety-critical systems, like autonomous cars or airplanes. So we have to argue about their reliability. One problem that can, for example, occur are adversarial attacks. So you have a stop sign, and then you add some noise to this picture, and then the neural network misclassifies this picture, leading, for example, to an accident. So there are many different properties you want to prove for neural networks. One is the equivalence. Assuming you have a sufficiently reliable reference network, then you ask the question, is another network, is my network equivalent to this reference network? This can be applied in many different areas. For example, if you want to reduce the size of a network, if you, for example, want to deploy it onto a device, or if you have additional training data and do not want to lose all prior guarantees. So our approach aims at proving or disproving the equivalence of two feed-forward neural networks. We do this by looking at a common input space with training data, then two networks that are either equal or not, which each has then an output. So the question is, are these networks equivalent? But we do not want to argue about number of nodes or edges or anything, but we want to argue about the relation from input space to output. So first of all, we only want to argue about relevant input. So we cluster the input space. The second point is that we need to find a notion of equivalence. So we define three novel notions. And then this whole approach is encoded into an NILP problem. And then given to a solver, in our case, Gurobi. The results can be shown in two different kind of areas. For example, on the left, you see we have an equivalence radii for different clusters, and we see the radius goes down when you increase the pruning of the network, so the size reduction. On the right, you see a counterexample, so a new data set or data point we generate, where the two networks classify a picture differently. And here you see, in my opinion, a picture of a 0, and the full NN classifies it as a 0, but the 20% prune network classifies it as a 6. So thank you for your attention, and if you have questions, comments, or are interested in this topic, please listen to the detailed talk, ask questions at the CP20 session, read our paper, and always feel free to contact us per mail.